Hey everybody, welcome to the shop on, what day is it? Sunday. I never know what day it is because I work 7 days a week and that's the way it goes when you have a small jet shop. This is the Arenda 10. It's been in the test cell and out. We are doing some post-run troubleshooting, evaluation, and head scratching. The Arenda 14, which is out of the frame because it's not over there. It's in the test cell right now. There may or may not be footage of that, but we'll see. I've been very busy. And a fairly common question we're going to look into today is about how do they make those things. And by those things, I mean these things. This one is the one that I'm pretty proud of. I cut that apart. I explained how I made it a couple years ago in a video called Air-Cooled Blades, I think. And we're going to take a closer look at this and some other examples and talk about how it was made. There's the, I guess the pressure face. So, and the cooling air hole inlet is right there. It's weird to do this backwards. Backwards. Yeah. Okay. So, let's do that now. All right, we have another camera that we're going to use for some close-up shots, but let's go through this from left to right, old to new-ish, sort of. This would be an example of a, well, maybe not first generation, how about second generation American jet engine. This is the J47, solid turbine blade, and very heavy, very thick, bit of twist to it. The fir tree mount there, and the infamous slot for the pins. Now, everybody asks, not everybody, a lot of people ask, how do you get the pins out? Well, that's included in 2 videos. And it's in the info section to all the videos talking about blade installation, blade removal, yada, yada, yada. The info section is a very good source of information. Yeah, that's an undamaged J47. Super cool. It's a single stage turbine. They all are. This is what it looks like when it's polished, and that's obviously, it's been dented. It's got an owie. Yeah. It's very nice. High nickel alloy. You could polish this to a mirror finish. It's just that polishing the inside is all done by hand and the fingers get sore. So there you go. That's the material that most of them are made of, or some variation thereof. This is 1940s metallurgy. Okay. The competitor, the Arenda. This is a polished Arenda blade. Similar alloy. Maybe the same alloy or maybe something slightly different. Again, not perfectly polished because it takes a lot of elbow grease. And it's very shiny, very nice. The Arenda, I think this is a 14, so this would be the second stage. It's bigger. The first stage will be here, this size. And they're non-air cooled, so they rely on the brute strength and temperature tolerance of the alloy and the moderate firing temperatures of the engines designed in the 40s and early 50s to help it survive. Yeah. Okay. Another leap forward. This would be, let's call this a 3rd generation, maybe even a 3.5 generation. This is the J79, stage 1. So the blades come in pairs. We'll look at this pairing situation a bit more later. I only have one of these. This is a brand new blade. Never been run. Oh, I'm wrong. I'm lying. These ridges on the, we'll show these in the close-ups. These ridges mean that it's been just slightly rubbing against the outer shrouds. So this has been nicely cleaned up and sort of hand polished. It's a J79 first stage, so that it's got one turbine. There's no low pressure, high pressure. There's just the turbine, but the turbine has 3 stages. 1, 2, 3. This is the first stage. This is the hottest stage. We ceramic coat these to make them last longer, but there's no air cooling holes in them at all. Cool. Now I think the next evolution, this would be again, I think this is from an Avon. I could be wrong, but I think it's from a Rolls-Royce Avon. And an early attempt at hot rodding the performance. There's the entrance holes for the cooling air. And there is an exit hole at the top. You see that? And there's no other holes. So this air would be forced in underneath the, what do they call them? Base base shrouds or baffles sometimes they're called. And so the air would come in here, go through the blade. There's only one exit hole. I don't know what's inside because I haven't cut one apart, but fairly simple. Here's the same thing polished up. 3 entrance holes and that one exit hole there. All right. Slightly more sophisticated, and this would be a design from the 60s. This is a small HP or high pressure turbine blade. And you've got the 4 little exit holes there and then like an entrance channel right there. Okay. And then we move ahead again in time. This is a Rolls-Royce Olympus. I think this is a high pressure turbine blade. Oh, I could be wrong, but anyway, it's got a tube welded in all the way through. I guess easier than drilling, and some sort of galleries or passages for the air to come out, and it's got a channel down here that the air is forced in. Maybe you can see. We'll show this on a close-up. It's got a line of exit holes on the leading edge of the airfoil. Nice big dent there. It's probably the reason this was rejected. Okay, Olympus, and then 2500. This is an example of how the blades come in pairs. This is a twin shank 2500. You have the fir tree slot and the disc, and these slide in there. It's a pair like that. They both have cooling air passages. These are the same as this one. This right here is, this is actually, there we go. There we go, now it fits. Okay, so that's a matched pair, and you can see the metal I had to remove very carefully to expose those air passages. Super cool. Okay, now the later versions of the LM2500, earlier? Actually, I'm not sure because I don't work on the 2500. I should know, I apologize. This is a single shank. It fits into the same slot, similar slot. The turbine, you can see it's a different size because the parts are not interchangeable between a single shank and a twin shank. It doesn't work that way. The turbine wheel is going to be different. This is an HP blade because it's short, it's fat, and it's full of air cooling holes. There's the inlets and the exits are there, top and there. This one has been just about melted. We'll look at that again on the close-ups. Here's another one that when you get greedy and you go for a bit more power, this is seconds away from disaster. As a matter of fact, the disaster was happening because it was hit by pieces of other blades and things smashing around in the engine. And these things are so incredibly tough that when they get dented, you know it's taken a huge amount of energy. I think this is a second stage, or this might be a later version of the 2500 or even a CF6 blade. Actually, I don't know where this one came from. It's larger, so it would be a second stage, but it's full of tons of cooling holes, so it must run very hot. It's quite beautiful. It's got a GE on it, so I'm going to guess it was made by GE, General Electric. This is another GE. This is from the F404, the F18, the CF18 or the FA18 engine. And it is in pretty good shape except for the loss of material along the outer tip here, which means it's had a very serious scrape along the shrouds that are in the engine cases that are supposed to seal against the tip, but they're not supposed to touch quite that hard. This engine this was taken out because it's junk now. It doesn't have the controlled exit of cooling air. It's just a wide open passage. So this happened. The engine must have been returned to depot, and this is garbage. And you don't weld this up and regrind it. This is a scrap blade. Okay, and then this one looks like a later stage in a 2500. It's got the heavy banding there of the rub. That's a bit more of a rub than I'd like to see, but hey, everything else looks pretty good. It's beautiful. Smaller cooling air hole and still lots of exits. On the thinner part of the metal, I guess, is more sensitive to temperature spikes. These have all been cleaned up to make them look nice. Yes. And just for fun, this is a LM2500 compressor blade. quite obvious it's a compressor blade because it's thinner. It's got less twist to it, much thinner. It doesn't run in the hot environment. And it's got a strong, but nowhere near as strong mount as the fir tree. Let's see, can I do that? There we go. Quite a bit different. And this weighs about, 1/8 as much as this thing. This is a very big, heavy piece. So, this is what I'd call an advanced course trick question. What the heck is this thing? It's got the fir tree. It's quite solid. It's a stainless steel blade. But look how much thinner and lighter it is. And look at how much less twist it has. See that? It's got less twist to it. What the heck is it? What is that? So you would get extra marks from me if you were to say, you don't have to tell me where it's from, I'll tell you where it's from. This is a compressor first stage blade from an Arenda Type 14. An old turbojet, the type I have in my shop right now. Part of the reason it's made of steel and part of the reason it's so overdone with the fir tree mount is A, because it is steel, it's a bit heavier, but this is overdone because back in the beginning of jet engine development and engineering, things were often done as good as they could possibly be done, and sometimes they went a little bit overboard. This thing is never going to come out of the mounts. It's awesome, it's incredible. It doesn't look like most compressor blades because it's just so there. It's just so much there. This is an awesome piece of machinery. Anyway, okay, hang on, close-ups. Okay, now the question why we're here, what we're doing this for today is how do they make that stuff? Well, the first turbine blades were forged, just like you'd forge any tool or engine block or crankshaft or something like that, because they're solid. And they were forged and they worked, and it was the best they could do at the time, and they quickly realized it needs to be better. So then they started doing cast turbine blades, and they were cast with regular casting didn't work because of the grain boundaries in the metal. Then they had what they call directional solidification, where the grain boundaries were all along the length of the turbine blade. That made it much stronger and much better. And then there was it's called single crystal blades, where the crystallization of the metal, the hardening of the molten metal, starts in a chamber below a divider with a tiny hole in it, and then the body of the turbine blade is above that. It's very carefully temperature controlled. So the crystals start to form, large crystals will start to form in the chamber below the division with the tiny hole, and only one of those crystals, crystallization regions, hits that hole, and then through that tiny hole and into the mold of the blade, it's a single crystal. So with a single crystal, you have no crystal boundaries, no grain boundaries, and it's amazing. So as a cast piece of metal, it's the best you can get. And single crystal alloy blades were made for a long time, and then they realized they wanted to make them run hotter. So they wanted to drill those passages. Sometimes they would use the lost wax process. So they would make a wax blank of the voids, mount it in the mold, and the single crystal would envelop the wax and wouldn't be wax. They would make another mold out of that, and then another mold where the wax shape would be made of plaster. Then they put the plaster in the mold and they'd single crystallize it, or the metal around the plaster, and then they would chemically remove the plaster with an acid which would dissolve it, and then it'd have these beautiful holes inside like we saw. I think blades have been fabricated with the core machined and the metal outer skin placed on there. I'm not sure how well that worked. And then a lot of the leading edge and the trailing edge holes, the tiny holes, we're going to see more of those in a second, they were drilled with lasers. Maybe they tried really fine drill bits, but it's very, very, very hard metal. It would take a long time. One of the reasons turbine blades are so expensive is they take a long time to make, And with the production methods I've been mentioning up to now, there's a lot of scrap. So you might start with 10 blanks and end up with 2 or 3 blades and the rest are garbage and they go back to recycling to try again. So that kind of quality control is leads to very expensive parts. Then the next breakthrough was what they call EDM, or electrical discharge machining. I used to call it electrostatic discharge machining, but it's not really electrostatic, it's electron current. It's a lot like welding in reverse. So you have your part in a dielectric fluid, an insulating fluid like a type of oil, and you have it grounded with an electrode to the circuit. And the drill, let's say, is a very tiny electrode, and it's held very close to a spot on your target, and it gets zapped like miniature lightning bolts. Typically it's not a constant flow, it's pulses. And each pulse of electricity causes the ablation of material immediately around the end of the electrode. So it's got to be very, very close. And the reason it's not a conductive fluid like water or an electrolyte solution is that would conduct the electricity from the whole electrode to everything. It would be like a battery. You want to pinpoint the electrical impact like a little lightning bolt, and you can drill tiny holes. It just takes a long time. It takes hours to drill them. Another reason why turbine blades are expensive, because there's hundreds of those holes. Okay, and somebody said today, those things are amazing. They look almost digital. Well, that is the stage we're at now because of the introduction of metallic 3D printing. Now, I don't know of any full-size gas turbine engine turbine blades made with 3D printing. Some of you might know, but I heard about and I read about and I watched a video about it. GE has made a small scale, a model scale, functioning, running jet engine out of entirely, maybe not the bearings, but what they say is entirely every single part was made with 3D printing in metal. So that to me would include the turbine blades. Once we can make turbine nozzle guide vanes and turbine air-cooled blades out of 3D printing, it's going to be amazing because the complex internal structure, it's like the floor plans of a skyscraper as you move up through the floors. 3D printing, you can do that easily, and it'll be amazing. So if any of you work for a company that does that, or if you're more up on things than me, because I work on old stuff. I work on the old hot rods. If you know of a modern jet engine, like the GE90 or the Trent or the Snecma engines, if any of those have 3D printed turbine blades, I'd be interested in reading some more about that, so lead me to it. And let's take a look at the close-ups of these blades now. Hang on. All right, this is the first in our collection here. This is the J47 solid. I'm thinking this was maybe forged. It takes a lot. There's not even any cracks on this surface. That's a very tough, very thick piece of metal. No cracking. Turbine blades are specifically designed for 2 things: toughness and strength under extreme heat. So there you go. There's the infamous pin slot. All right. The Arenda, very similar thing. It doesn't tell you in the overhaul manual or anywhere how it's made. Okay, this is another J47 solid, and I don't know if you can see it. You probably can't see it, but the front edge, the leading edge of this blade, has a lot of little cracks in it. A lot of little cracks. Can you see them? Maybe not. Anyway, that's why I kept this one. Never to be used again. And I kept it for educational purposes, otherwise it would have been thrown away. Okay. LM1500 or J79. You can see the striations on there? That's from the, let's see if we can get the light to just shine off it. Yeah. There we go. That's from rubbing against the tip shrouds. And These are what they call shrouded blades, where the shrouds are attached to the tip, and it's to seal leakage around the edge. So these do run in a seal, but there's more of a positive seal. Of course, the disadvantage is you've got extra weight at the worst possible place in a spinning part of a machine. Yeah. There's our exit hole. And we move on to our tiny little smaller engine HP turbine blade. You got the fir tree, the passage, and the cooling outlet holes. I actually engraved this. Can you see that? Rolls-Royce Olympus. 2024 is not the date. I'm not returning from the future. That's the model number of the Rolls-Royce Olympus, and it was designed in the 60s, I believe. Those are the holes that were probably drilled by laser beams, lasers, possibly tiny drills, but I think you can, if you look at it closely enough, you can see a slight irregularity in the alignment, and so I think that's from the lasers. Just they're so small, and it just blasts it so much that I think that, I don't know. I think I'm just babbling here. And there you've got the welded tube in there for the cooling air, and welded tube that near the leading edge. On the other exit passages. This is the one I made. You can see how thin and how long those trailing edge holes are. That's just amazing. Pretty sure those were EDM'd, because the laser causes the material to melt a bit and distort. I'm sure lasers are great, but EDM is probably better. These internal passages would be made with some sort of a core. Like I said, the plaster core, which would be chemically eaten out once this cooled and was removed from the mold. A very lengthy process. Some more film cooling holes. Maintaining a layer of air between the hot gases pushing against this and the metal itself. So it's insulated by a jacket of air, and it's cooled inside by air convection cooling. There's the entrance holes. Super cool. And the single shank version, slightly different, but the engine is still called an LM2500. There's your trailing edge exit holes, and some of them are obliterated here. This is when you got a bit of a lead foot and you're asking for 36,000 horsepower from your 34,000 horsepower engine. You can see the melting and the distortion and basically the caving in. This is that's not how you drive your car. That ain't good. And here is the same thing, just worse. This is now allowing cooling air to escape through this big gash, and so it's not coming out in the little ones. And it hasn't, you don't see a lot of burning here, but it was only moments away. Moments away. And it was hit by some debris. Pieces are smashed out. You can see the distortion there from being dented and hit. Quite amazing. And they're all similar alloys, but similar but different. Metallurgy improves every year, every month probably. There's a lot of cooling air entrance holes there. We don't know what the exit holes look like because they're ablated, they're gone, they're worn off. Leading edge film cooling holes, and also on the pressure surface. These little things, you see those? They look like they're designed to hold a plate, a base plate that helps to seal this joint with the next blade. So it'd be intricate for the assembly, but it's all worth it in the end in your super high performance. This is out of an F-18 engine, an FA-18 or a CF-18. Not the Super Hornet, but the Hornet. Yes. Okay. Now we've got our, look how similar our compressor blade is, our steel compressor blade. I think it's stainless steel with, for example, this is a J47 turbine blade made of nickel alloy, much heavier. Let's see, we'll get them both. There's the leading edge shot of the compressor blade. on the turbine blade. But they could sure fool you, couldn't they? So that's amazing. I would make that a practical exam question, a trick question for the advanced extra bonus marks. And a good answer for this would not be where it came from, but just a description of the characteristics. It's much thinner and lighter than a turbine blade. Let's get a better profile. They seem the same. It's got a much less of a curve to it, but at the base, this one's about a 1/4 inch thick. This is about 1/8 of an inch thick. So, what? 3 millimeters here and 6 to 8 millimeters here. Otherwise, they do look very similar. Okay, we've talked a little bit about the different developments in the history of turbine blades and air-cooled blades, a little bit, and how they're made, sort of, maybe. But at the very least now, you'll be able to decide whether or not it really is what it says it is when you're looking on an eBay item for sale that says jet engine turbine blade. Because usually it's not. Usually it's a stator, a compressor stator. So now that you're an expert, you can sort out the fact from the fiction, the EDM from the whatever. All right, on a Sunday, in front of an Arenda 10, glorious turbojet engine with the green go stick. I repainted this because it was about 4 layers of paint deep and it looked like garbage. Green for go, green for go. Thanks for watching.